you remember from Gen Chem, right after we talked about Thomson and the electron, we went on to talk about Rutherford and the idea of the nucleus. But before we get to that, which we will, I want to talk about radioactivity, because radioactive emission is actually one of the things that allowed Rutherford to study the atom the way he did and describe the nucleus.
All right. So, found out quite by accident, okay, aka
Serendipity, which is the word that gullible people use to describe coincidence.
right?
It just happened to be this way. There's no particular reason that it happened. It just happened.
So, found out by accident that a piece of mineral containing uranium, right? So, a mineral, if you're into geology, it has several different atoms in it, arranged in an important quaternary structure. But there's uranium in it, and that mineral could produce its image on a photographic plate in the absence of light. And if you guys don't know, this is actually the foundation for what we call X-rays today. Not the high energy form of light, but X-rays in the sense that you break your leg, you go to the doctor, they take an X-ray of you, right? And they develop that photographic plate in the absence of light, because that's what you do with photography. But it would produce its own image. This was called radioactivity.
Okay, because it happened in the radius, the close proximity of the
Particular thing, and it was activity. There was stuff going on. And it was attributed to the spontaneous emission of radiation by the uranium
in that particular mineral.
Now, there are 3 types of radioactive emission. So this spontaneous emission that comes out of
A uranium atom is just one type. And there are 3 types of radioactive emission.
There's the biggest type and the safest type, which is called alpha emission, right? It's equivalent to a helium nucleus. It has 4 protons. It has 2 protons, 2 neutrons, for a mass of 4. And so this is the largest particle that radioactivity can produce. It is 7,300 times the mass of an electron. Okay, it's really large. It's denoted
with the helium symbol.
And since it's larger than everything else, early atomic studies usually focused around these.
Because they were large enough that they were easy to use, easy to identify, easy to produce, easy to measure. Also, because they're so large, they can essentially be stopped by almost anything. Just like a regular old piece of clothing will actually stop an alpha particle from penetrating any deeper
than it is already. Then we have beta emission, right? Beta is essentially a high-speed electron. And as an electron, we know that because this type of emission, can be denoted in either of these 2 forms. Because remember, it is essentially a high-speed electron, so we can represent it as an electron, or beta emission, so we represent it with a beta. It has no mass. Notice how there's no mass. The total mass of this alpha emission, this alpha particle, is 4. Total mass of this beta emission is 0, but it does have a charge, right? It does have a charge, so minus 1. This one is a little bit more. It's actually quite a bit more dangerous than alpha emission, but not nearly as dangerous as gamma radiation. And yes, that is the letter gamma. Gamma radiation does not have representation like beta or alpha emission. It just has that letter gamma, because it's pure energy. There's no particle. There's no protons. There's no neutrons. There's no charge. It's simply energy. But because of that,
it's by far the most penetrating and by far the most dangerous, right? Remember, gamma rays made the Hulk, right? It's a big deal, very, very powerful.